Okay, let's take a look at chapter 5. We are talking about integration. Three different names for integration. First one, integration. The same thing as saying antiderivative. Also, you can call that integral or indefinite integral. So they all equivalent is basically integration. And let's take a look at antiderivatives really quick. Antiderivative is the inverse process of finding a derivative. And when we talk about derivatives, we know the original function. Original function is given, and we find derivative from there. But for the antiderivative, since it's inverse, so now we know the derivative. So derivative is given, and we find the original function. That's why it's the inverse process. Okay. In this, we're going to learn how to write the general solution of the differential equation. We're going to use indefinite integral notation for antiderivatives. And we're going to apply some basic integration rules to find antiderivatives. And we also find a particular solution of a differential equation given initial condition. Given the initial condition. So again, let's get to the antiderivatives. Supposedly, right, you ask to find a function, original function f of x. F here indicates f of x, whose derivative is f prime of x is 3x squared. So here f prime of x equals f of x equal to 3x squared. So we know that if original function equals x cubed, then the derivative of that, apply the power rule, and it becomes 3x squared. So in that case, we know that the original function must be x cubed. So now here, capital letter f of x is the antiderivatives of f of x. So function capital letter f of x is antiderivatives of function f of x on the interval I if f prime of x equal to f of x for all x in the interval I. In terms of the representation of antiderivatives, if f of x, capital letter f of x, is an antiderivative of f of x on the interval I, then g of x is an antiderivative of f of x on the interval I if and only if g of x equals to capital letter f of x plus c. For all x in I where c is the constant. So let's take a look at this. If g of x equal to x cubed plus 1, So g prime of x, derivative of x cubed is 3x squared, derivative of 1 is 0, so it's still 3x squared, and this is still g prime of x is also equal to f of x. So that means the antiderivative is not unique. Also, what if g of x equal to x cubed minus 1, then g prime of x is equal to x, derivative of x cubed is 3x squared, derivative of negative 1 is 0, so still 3x squared. So again, that means g prime of x equal to f of x. So this constant at the end, any constant will work, right? Will also give us the same derivative. So that means antiderivative is not unique. Usually we have infinitely many solutions for antiderivatives. Basically g of x equal to f of x plus c. Any constant c will work. That will give us infinitely many solutions. Meaning infinite many solutions. So you can represent the entire family of antiderivatives of a function by adding a constant to a given antiderivatives. For example, looking at derivative of x squared equal to 2x, you can represent a family of all antiderivatives of f of x equal to 2x by g of x, which is x squared plus c, because the derivative of constant c becomes 0. Derivative of x squared becomes 2x. So that will always satisfy the requirement. So this is what we call x squared plus c, is what we call the family of all antiderivatives of f of x equal to 2x. Where c here is a constant. And this name, generic name for constant c, is called constant of integration. Very unique name, constant of integration. So when you try to find the antiderivatives of indefinite integral, you always need a constant c in your answer. Okay. So g of x equal to x squared plus c is the general solution of the differential equation g prime of x equal to x. Okay. And we call g prime of x equal to x a differential equation. Some of you guys may need to take this course called differential equation. So basically just given derivatives or second derivatives, and you need to go back to the original function. A differential equation in x and y is an equation that involves x, y, and then derivatives of y. For instance, y prime equals 3x and y prime equals x squared plus 1, a typical example of the differential equation. Alright, let's see. Let's find the general solution of the differential equation y prime equal to 2. So in order for y prime equal to 2, y must be equal to 2x. And since we're talking about general solution, so adding c at the end, right? So the answer should be 2x plus c. And if you want to check it, just find the derivative, right? Y prime derivative of 2x, make it 2. Derivative of constant c, make it 0, right? So that will become 2. Okay, so checked. So the answer is just 2x plus c. As you can see, since we know that derivative equal to 2, that means slope of tangent line is equal to 2. So slope of tangent line equal to all these lines. You have infinitely many lines which has a slope of 2, right? You can draw as many as you want, right? As long as it's parallel to that. So you basically can draw infinitely many lines which satisfy this condition. Depends on what c you're trying to substitute, right? So c could be negative 20, negative 10, negative 5, negative 1. C could be 0, C could be 1, 2, or 5, or 10, or 20, or 100, something like that. So that's why you, for antiderivatives, you always end up with infinitely many solutions. So the notation for antiderivatives, we always write like this: antiderivative f of x dx, which becomes f, capital letter F of x, which is the original function, plus c. That's a very typical notation for antiderivatives. When solving a differential equation of the form dy over dx, so y prime, another way of writing y prime dy over dx equal to f of x, and dy is equal to f of x times dx. And the operation of finding all solutions of this equation is called antidifferentiation or indefinite integration. It's denoted by using an integral sign. And the general solution is denoted by y equal to integral of f of x dx, and you end up with the original function, capital letter f of x plus c. C is what we call a constant of integration, and dx is what we call the variable of integration. F(x) is the integrand, and capital letter f of x is the antiderivatives of f of x. In the expression integral f of x dx is written as antiderivative of f with respect to x. So the differential dx serves to identify x as the variable of the integration. The term indefinite integral is synonym for antiderivative. Let's take a look at the basic integration rules. So we know that integration is the inverse process of the derivative. So let's just put the differentiation rules and the integration rules side by side so you can compare them. The inverse nature of integration and differentiation could be verified by substituting a prime of x for f of x in the indefinite integration. So integral of f prime of x dx is equal to f of x, because integration is the inverse of differentiation. So as you can see, if we put derivative and an antiderivative together, these two will cancel each other. So you end up with f of x, right? because derivative and antiderivative, they will offset each other, just like plus, minus, or multiply or divide, right? It's inverse of the, due to the nature of differentiation, it's the inverse of the integration. And let's get to the technical part of the integration. First one, let's review the differentiation formulas. Derivative of a constant c is 0. It's constant rule. Derivative of k of x, linear terms, just becomes k. Derivative of k times f of x becomes k times f prime of x. Derivative of f of x plus minus g of x becomes f prime of x plus minus g prime of x. Derivative of what? Exponent. So we put a exponent in front, so n goes in front to reduce the power by 1. So n times x, n minus 1. And let's take a look at integration rules. So the antiderivative of 0 with respect to x is going to be c, right? See, go back to original function. Antiderivative of k with respect to x becomes k of x plus c. Antiderivative of k times f of x dx becomes k times antiderivative of f of x dx. Antiderivative of f of x plus minus g of x dx becomes antiderivative of f of x dx plus minus antiderivative of g of x dx. And in terms of power rule, antiderivative of x to n dx is equal to, now you add a 1 to the exponent, so it becomes n plus 1, the exponent becomes n plus 1, and the exponent also becomes the denominator, so x n plus 1 over n plus 1 plus c. Okay, so this is the power rule, very important. We use it very frequently. And one thing is n cannot be equal to negative 1. If it's n equals negative 1, then negative for the outcome x raised to n plus 1 over n plus 1, denominator becomes 0, and the whole thing will be undefined. And derivative of sine x becomes cosine x. So the antiderivative of cosine x will become original function sine of x, n plus c. Derivative of cosine x is negative sine x. So the antiderivative of sine x dx with respect to x will become negative cosine x. And derivative of tangent x equals secant x squared. So antiderivative of secant x squared dx becomes tangent x squared. Derivative of secant x equals secant x times tangent x. So antiderivative of secant x times tangent x dx with respect to x becomes secant x plus c. Derivative of cotangent x equals negative cosecant x squared. So antiderivative of cosecant x squared dx with respect to x becomes negative cotangent x. This negative sign comes from here. Okay. Derivative of cosecant x is equal to negative cosecant x times cotangent x. So the antiderivative of cosecant x times cotangent x dx becomes negative cosecant x. Again, this negative sign comes from that. So let's try to find the antiderivative of 3 of x. So what we do is we're going to write antiderivative of 3x with respect to x. So now you can put a coefficient in front, x dx, and you can put back to the exponent x to the first dx. Now we apply the power rule. You're adding 1 to the exponent, and the exponent becomes the denominator, 1 plus 1 plus c. Okay, so always add c at the end. So it becomes 3x squared over 2 plus c. That will be the general solution of this, of the antiderivative for 3x. In this case, c could be any number, right? Any constant. So the general pattern of the integration. First of all, you start with the original integral. You set up the integral. Rewrite it. And then apply some integration rules to integrate it. And after that, simplify it as much as possible. And this flow chart shows you the general procedure of finding the antiderivative. So let's take a look at, so as you can see, for any antiderivatives, we end up with the general solution. But in engineering or other field, sometimes you need to find a unique solution or particular solution, unique, given the initial condition. Okay, so let's take a look at this example. We know that the antiderivative of f of x dx has infinitely many solutions. Infinitely many solutions. But sometimes, you have to figure out the unique solution. So let's say antiderivative of 3x squared minus 1 dx, which is equal to x cubed minus x. We can do here 3x squared minus 1 dx. First of all, you can separate them. 3x squared dx minus integral of 1 dx. First one, apply the power rule, put a coefficient in front, add 1 to the exponent, and put the exponent as the denominator. And antiderivative of x becomes, antiderivative of 1 becomes x, and c. So now you get 3x cubed over 3 minus x plus c. Cancel 3, x cubed minus x plus c. That's how they end up with this particular general solution. And as you can see, with different constant, you end up with different graphs, right? And on this particular graph, you can see that but if, let's say, we know a given condition that for the original function f of 2 equals 4, that means given point on a graph 2, 4, then basically we will be able to find out the unique solution here, or particular solution. So given this point, given point is what we call the initial conditions. And since we know that a general solution is this, and given an initial condition, this curve passed through 0.24, that means f of 2 equals 4. So all we can do is replace x with 2. So we get here x becomes 2. So we have 2 cubed minus 2 plus c, which equal to 4. This is a minus 2 plus c equals 4. 6 plus c equals to 4. Subtract 6 from both sides of the equation. So c equals to -2. Now we know that the unique solution here, f of x, is equal to x cubed minus x minus 2. Okay? For c is equal to -2. And this is what they call the particular solution, or if you want, you can say unique solution. Which satisfy the initial condition Now let's take a look at another example, right? Find the general solution of f prime of x equal to 1 over x squared. Here x is greater than 0. And find a particular solution that satisfies the initial condition. Again, you see the keyword initial condition, f of 1 equals 0. That means the curve of the original function, the graph of the original function passes through 1, 0. So the very important thing is find a general solution first, right? So we're gonna do f capital letter f of x equals to antiderivative of f prime of x dx. And replace f prime of x with 1 over x squared dx. And then you gotta apply the power rule. Let's rewrite this as the exponent. You flip this to the top. It becomes x to the -2 power. This goes on top. Becomes x to the -2 dx. Now you can apply the general power rule. So x -2 plus 1 over -2 plus 1. So as you can see, that from the general power rule, the exponent and the denominator must be the same, right? Just keep that in mind. And adding c at the end. So you end up with the x raised to -1 over -1. And flip this to the denominator. It becomes -1 over x to the first. So just -1 over x plus c. So this is what we call the general solution. So in order to find a unique solution of particular solution, given that f of 1 equals 0, now we know that f of x equal to -1 over x plus c. So now for that equation, replace x with 1. So -1 over 1 plus c equal to 0. So -1 plus c equals 0. Isolate c, adding 1 from both sides of the equation. So c equal to 1. Right, so now we end up with a c equal to 1. That means the unique solution f of x must be equal to 1, -1 over x plus 1. Okay. So this is the particular solution, or the unique solution. And in the background is the detailed solutions. As you can see, general solutions has infinitely many general solutions, but for particular solution it's always unique. So only one given an initial condition you always find the particular solution. Okay, that's pretty much it for this particular section.